we're going to introduce the very important concept of multiple linear regression, build upon the ideas of simple linear regression, but adding more than one predictor variable. You can take an entire course in multiple linear regression. Some of you, hopefully most of you will, but we'll also do a quick introduction in the next couple weeks. Remember that simple linear regression allows us to draw a line and fit a model between two continuous variables. We can predict the mean value for a given x by using the slope. For every 1 unit increase in x, how does y change on the average? We saw that the slope and the intercept define the line, and we can test null hypotheses around that line as well. We can use the correlation coefficient and the coefficient of determination, r squared, to think about how tight the points are around the line. And the standard error of the estimate, also known as the root mean square error, can tell us the standard deviation around the regression line. And of course, remember, the first thing we always do when we get data is we look at our data. We're going to look at some new data now about babies. How big is a baby? And here are some real data from low birth weight infants born in Boston. And on these data, we have the gestational age of the baby and then the birth length. And with the simple linear regression, we can ask questions like, is gestational age a significant predictor of birth length? We can say, how does gestational age predict birth length? Or what is the relationship between these two things? And I think you'll appreciate that for this, we say we can just run a correlation and see if it's significant or not. But here, we can think about the slope and how the slope can tell us a little bit about the dose response here. We're going to build upon this example with multiple regression. A quick Stata review. At this point, you're probably coding a lot of the work that you've done, or you might be doing point and click. In Stata, to do a graphic, we can create a two-way graph, and we have our y variable, which is our outcome, and then we have our x variable, which is our predictor. To run a regression model, we can go through the statistics tab and point and click our way through it. Or we can just use that verb regress y on x. So for our simple linear regression here, regress length on gestational age, and we get this model. Here is our intercept, 9.33. This shows us the dependent variable. Length depends on how long you're in there cooking. So length equals 9.33. And then we see the coefficient here, or the slope, 0.95 gestational age. For every 1 unit increase in gestational age, on the average, a baby is 0.95 bigger. The root mean square error, which we see up here, which again is also called the SEE. That's not my fault. It's confusing that there's two names for it, but it's what it is. That tells us the standard deviation around the regression line. So if you go in, and the doctor says, how pregnant are you? 32 weeks. Here's my prediction. Plug it in. You have to acknowledge that that prediction isn't perfect. There's still some leftover or residual. And the standard deviation around that, 95% of women like you will have babies of this given size. That's the SEE, or the root mean square error. We also have the R squared. 45% of the variability in birth length can be described simply by gestational age. Lots of other things go into it. Genetics, drug use, what your grandmother ate when your mother is in the womb, right? The epigenetics. But 45% of the variability can be explained or is due to just this variable alone. We're going to build off this to do multiple linear regression. Most of this is going to look the same. We still fit slopes and intercepts. We can talk about the standard error of the estimate for the accuracy of prediction. We can talk about the R squared for how much of the variability is captured by the model. We still have independent and dependent variables, and we still have some sort of leftover or unexplained. But what we can do now is add more than one predictor variable. How is birth length predicted by gestational age? And can we put maternal age in the model too? Now, this is written in terms of the population. The Greek letters here show you that we're talking about what is the true relationship from the intercept, A or alpha, from the slopes, B or betas, and then we see this E here, which stands for error, that there's always going to be some kind of leftover variability. Multiple regression will help us sort of tease out, can we capture some more of that variability? Can we explain more by adding additional predictor variables into the model? First, we're going to have to see what multiple linear regression looks like.